one.
Okay. Hi, everyone. So today, me and I'm Anish, and we'll be talking about automatically explaining fuzzy cognitive map simulation scenarios using uh, pre-trained models. So before we start what our project is about, you as a uh, reader need to have some kind of background on cognitive map, what are fuzzy cognitive map, and how they are used in simulations. So in the most layman term, uh, cognitive map or a concept map is a network of concepts. So they are interconnected to each other. For instance, this here shown is a subsection of a childhood obesity map created by Allender et al. In 2015. So they this map actually has around 100 nodes, but this is only a subsection of it. And they are created through a process of what we call participatory modeling. So subject matter experts from different fields come together to build a concept map around a certain problem like obesity. So that's causal maps. And as you can see that there are causal relationship between the concepts. For instance, if you see health literacy, increase in literacy will increase uh, healthy school curriculum. So that's one of the causal relationship that is reflected by the concept map. Fuzzy cognitive maps are an extension of concept maps. So unlike concept maps, fuzzy cognitive maps are quantitative in nature because here the concept are going to have some kind of values, quantitative values, and also the relationship are also going to have some kind of causal strength, which is again quantitative. So if we have an initial scenario where each of these concepts have a certain value associated with them, and we pass it to the FCM, we can let it run and we can get a final state of what the FCM is going to produce. So that's how FCMs can also be used in simulations. Uh, so now, Azura.
Okay, so the actual problem in question is we are trying to use a fuzzy cognitive map, which was just explained as our input to our simulation here. So that's the information we're taking in. And we are using tools in Python and with OpenAI to generate text. And we're using the obesity data uh, as our sort of example source for this. Just that's what we've been working with. And um, essentially, our goal here uh, is we want to be able to take a fuzzy cognitive map, and whereas normally what has to happen in order to analyze a fuzzy cognitive map is you will need to have someone who's familiar with the subject matter and knows how to read FCMs. They will need to manually look it over as a human, and they will need to write up an explanation of it, translating all of it into plain text. What we want is we want to set up a simulation model that can take the data from an FCM and directly convert it into a readable and comprehensible explanation just based on that and the input values so that there doesn't need to be any human intervention and that it can be a more streamlined process.
So far, like all of us have gone through three milestones. So in our first milestone, what we did was try to get familiarize ourselves with an older project, which is the base of the current project that we're doing, where they were trying to explain, do the same thing, but they were trying to explain a causal map instead. Uh, in the second milestone, what we did was we read through the papers on different kinds of FCMs and what different kinds of author and their styles of writing or explaining FCMs or fuzzy cognitive map simulation scenarios were. And also we also looked into uh, graph to text uh, papers where we tried to extract ideas of converting our FCMs into text. So in the milestone 2, each of us came up with individual architectures, and which has been combined to propose a final architecture for the current milestone. So the rest of the milestone 3 are going to be talked about in the further slides. So this is the final architecture that we came up with. So here scenario, FSIM scenario is the initial simulation input that we provide, and it needs to be encoded into some form of linearized representation. So as I mentioned previously, scenario is all about quantitative data, and whereas linearized representation is going to be more textual format or textually encoded format. And each of these are going to be augmented using processes like permutation and templates, which we will be talked about later. All of these combined data are going to be used by GPT-3 for training. And finally, they will pass through 2 different evaluation phases, which are going to be automated evaluation and human evaluation.
Hello, I'm Caleb Anderson. My role in this milestone, or part of my role in this milestone, was creating our permutation. So basically, due to the nature of what we're doing, our data set is generated by us, the people working on this project. So it's really hard to generate like a lot of training data. So one thing that we're strategizing to solve this problem is doing a bit of permutation. So basically we'll take one scenario or one set of training data and then permute it. And right now, basically we take 7 random permutations of each scenario that we're using, each scenario being the linearized sentence generated from the key value pair. And yeah, basically the reason that we're doing this is because on our research prior to this milestone, we saw that other researchers who were doing similar text simulation models found that using this type of permutation strategy actually generated better results, particularly using the GP2 and GPT-3 algorithms.
Right. So I'm Josh Kreil, and I did the templates. So basically, with the templates, you are going to start by passing a dictionary with an attribute and value, and then you see what templates that attribute could be applied to. With this approach, we can generate multiple new sentences off of a single dictionary, which is going to be improving our data, hopefully. The templates are something that we all made together. Each of us made 3. Here, a template is a sentence with values taken out and replaced with a curly brace with an attribute inside of them, or in some cases, multiple attributes separated by an underscore, but we only do up to 3 attributes being combined at one time, and all of those attributes have to have a tolerance of at least 0.1 of each other. And then from that, we find the template that will work with our dictionary of attributes and get a result like the one shown here. The curly brace spots are replaced with new values chosen randomly from the generic map from their associated value. And from this, we hope to increase our sample size and hopefully increase the accuracy of our results. Also, we are thinking about possibly changing to a more specific map, as the generic one works, but it doesn't make much sense for something like age to be very high or very low. It makes more sense for age to be young or old. And then another issue is it would be something like conjunctions. As you can see in our results, we have an although, but everything in that sentence is high, and the although should indicate that the knowledge would be low because the other 2 items are high.
So for our evaluation criteria, we're using both the BLEU score and the Meteor score. Like other precision or accuracy metrics you've seen in the past, the values range between 0 and 1, with values closer to 0 being like bad accuracy, bad quality, and values closer to 1 being good accuracy, good quality, good precision, and whatnot. So this is kind of a breakdown of at least like the BLEU scores, what you can expect from the different values. And so far, as you can see, we have pretty good scores. And the difference between the BLEU 1 through 4 scores, just has to do with the n-gram overlap, which is their precision metric. So for an example, a unigram, which would be your blue 1 score, like a unigram would be like the occurrence of a single word within a sentence. So I would be a unigram and love would be its own unigram. Whereas for the blue 2 score, which is a bigram, it would measure the occurrence of like a 2 words or a phrase. So I love would be a bigram together. So unigrams are going to account more for your accuracy, and the longer your n-grams are, that accounts more for the fluency of your translation when comparing your produced sentence to your reference sentence. So we have pretty good scores here right now, but this is kind of awkward given that we're pretty early into this project or this implementation. And so we think that this could be due to repetitiveness of our training data or our sentences. And to try and fix that, we want to like go over them, make sure that we can mix them up a little bit, just give it a little human evaluation. And we've individually produced 20 explained scenarios. So in total, we have 100 explained scenarios, and we've each created 3 templates. So we have 15 templates in total. I think 11 out of the 15 were used so far. So one thing that we could do to probably like improve the quality of these scores is also like generating better templates, or using more templates. And then we had 640 permutated scenarios with 512 training samples, 90 validation samples, and 38 test samples.
So far, we have gone through a good chunk of the our entire project, but still, these are some of the steps that needs to be taken in the upcoming milestones. So the ablation study here, what we want to perform is how much permutations or templates are contributing to the improvement or degradation of the results. And also we'll have to start documenting our work, our research, what we studied through, and what we are expecting further to do. And one of the important component that is missing is human evaluation. Right now, we are only performing automatic evaluation using Blue and Meteor, but we want human evaluations as well, because automatic evaluations do not always truly reflect the goodness of AI generated text. And in order to validate our study, we also want to expand our work into other FCM case studies. Right now, it's just working in the obesity. So we want to find another FCM case study so that we can validate our work. So that wraps up our milestone 3. Thank you.